Hiya Pirates, what we're going to do today is we're going to try to see if we can't figure out the specific heat of a piece of unknown metal. As you can see, I've got a weight inside a beaker of boiling water that is here. So that weight is sitting in there, and I don't know what metal that weight is made of. And so I want to be able to figure out what its specific heat capacity is. So what we're going to do is we're going to take that piece of hot metal and we are going to put it into some cool water here, and we're going to get an energy exchange. And then because we know everything about the water, we should be able to deduce the identity or the specific amount for that metal. So what we're going to do here to start, again, sorry about the confuso vision that is here, but trying to film and do math and do everything by myself is very difficult. So what I've got here is I've got 100 milliliters of water, and I'm going to take that and I'm going to put it into our very high-tech calorimeter that is here, which is just a styrofoam cup. I am then going to take the temperature of said amounts so that I know exactly what the temperature of that is, and give that a second to think about what it's done. By the way, since we're letting that acclimate, this is 100 milliliters of water. The density of water is 1, so because of that, then we also got 100 grams of water. So I've got 100 grams of water in here, and according to this thermometer, it is starting right at about 24.5 degrees Celsius. So we are starting at 24.5 degrees Celsius here for 100 grams of water. Now, what I'm going to do now is I'm going to take the thermometer and I am going to put it into my boiling water, because I can't necessarily assume that it's going to be exactly 100 degrees Celsius, which is where it should be, but it should be within a stone's throw of that. And while we are waiting here for this guy to go and get up to its maximum temperature, you should know that the weight inside of there, I've already pre-massed it, it has a mass of 200 grams. So the actual piece of metal in there has a mass of 200 grams, and it's going to start here in our boiling water, which is at 99. I'm just going to go ahead and call it here at 99. So what we're going to do now is we are going to take this piece of metal and we are going to put it into our calorimeter that has water. The metal is going to give up energy. The water is going to absorb that energy. However much energy the metal loses, because it's an exothermic process, should be the same that the water gains, because it's an endothermic process. And if we know how much energy the water gained, we can figure out how much energy that the metal lost and work backwards and figure out what the specific heat capacity of it is. So I have got here my piece of metal, and I'm going to take my tongs. And when I take my tongs and hopefully not drop it, I'm going to, as quickly as I can, transfer this, because every second that this spins outside of the water here, it's losing energy to the air, which is a source of error in this experiment. So I'm going to try to do this as quickly as I can. Ready? 1, 2, 3, go. And there we are. Boom. There it goes. And I'm going to put the lid on like so, and then put in my thermometer there. Then what I'm going to do is I'm going to stir, stir, stir. And as I stir, 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 it will let everything acclimate. And the temperature of the water should be increasing because the temperature of the metal is decreasing. Again, endo and exothermic situation. And if I give this long enough to acclimate, once they reach the same temperature, then that means that they are in thermal equilibrium with each other. And what do you bet we can figure out what the heat is? All right, that's probably enough time. I'm going to go ahead and take the lid off, and it looks to me like the temperature is up to 38 degrees Celsius. 38 degrees Celsius here. So our water started at 24.5 and went up to 38. Our metal started at 99 and went down to 38. Using that information, you should be able to figure out what the specific heat capacity of the metal is, and let me show you how with some calculations. All right, so what we're going to do now is we're going to do some calculations. So what we've got here is we've got a calorimeter with some water in it that is at a certain temperature. What you're then going to do is you're going to take that piece of metal and you're going to put it in there. Now, keep in mind that the metal was hot. So that hot piece of metal is going to give off energy like so, because it's going to be exothermic. And then the water that is here, it is going to gain that energy, and the water is going to be endothermic because the hot metal is giving it off. But regardless, however much energy the hot metal gives off, the cold water should gain. It's just in the opposite direction. So that then leads us to this equation, which we already know, which is that Q lost is equal to negative Q gained. So whatever heat that is lost by one is equal to the heat that it's gained by another, but you have to throw in a negative sign because of the opposite direction. Now, nowhere in this experiment are we dealing with any phase change. So we're not talking about melting, freezing, boiling, condensing, sublimating, or depositing. And so consequently, our Q for each of these circumstances is just going to be MC TF minus TI, final minus initial. And that's of the energy that's lost by the metal. And that's going to be equal to negative MC TF minus TI that is gained by the water, right? So all we have to do now is plug in all of our information. So quick reminder of all of our data. Now for our metal, it was 200 grams to begin with. We don't know what the specific heat capacity is. That is going to be X. That's what we're looking for. The hot piece of metal started at 99, and by the time it cooled down, it was at 38 degrees Celsius. The water, I had 100 milliliters of it, which means that because it's got a density of 1, it's 100 grams. I'm going to assume that the specific heat capacity is 4.2 joules per gram degree Celsius. I could throw it as 4.184, but honestly, there's so much error in this, I may as well just keep it simple and call it 4.2. The water started at 24.5 degrees Celsius and ended at 38 degrees Celsius. So I now have everything of all 8 of my variables except for the specific heat capacity of the metal, which is going to be my X. So I'm going to go ahead and start plugging numbers in. So the mass of my metal is 200 grams. The specific heat capacity is X. Now careful on this, because our brains want all of our numbers to be positive, and so sometimes you'll mess yourself up by inadvertently switching numbers around when you shouldn't. The metal started at 99 and ended at 38. So the final is 38 and the initial is 99, but that's going to leave a negative number. Yeah, it should, because it went from 99 down to 38. The temperature change should be negative because the temperature of the metal went down. So then that is going to be equal then to negative, and now we got to put in our water information. And remember, here's all our data for the water. I had 100 grams of the water. Water is 4.2 joules per gram degree Celsius, and the temperature change for the water is positive. It ended at 38 and started at 24.5. That's there. So you get out your calculator and you do a little mathification. I'm getting negative 1220 times X is going to be equal to negative 5670 here. Sorry, handwriting is bad. That's 70. And now, in order to solve for X, I divide by, ooh, that's the wrong number there. I think it was 12,220. Hold on one second. 38 minus 99 is that times 200. Yeah, there was another 2 in there. I apologize for that. 12. Get my numbers right here. Silly. 12,200x. I apologize. All right, so then we're then going to divide by negative 12,200. Almost did it again. Divided by negative 12,200. And so then I've got 5670 divided by the 12200. I'm getting a specific heat capacity of about 0.46 joules per gram degrees Celsius here.